Hey, so today what we'll be doing is we will be refreshing the concept of broadcasting. So what is broadcasting? Broadcasting is the ability of taking one matrix and basically making it compatible with the other, as long as that one matrix is like a unitary matrix or a single dimensional matrix. We'll go over the rules. We have already done it, but this just formalizes the rules that we did in day one. So let's actually get started. So we will do first is broadcasting with a scalar, right? So if we were to take x, right, I will again import torch over here. Let's say x is equal to torch dot tensor. And what is our tensor now? 1, 2, 3, 4, 5. So this is a single dimensional matrix, right? But now let's say we have a two-dimensional matrix. So this is 1. And then you have, there you go, 6, 7, 8, 9, 1. Okay. So you have this whole new matrix. So now if you write over here, print x dot shape, and you will get it is 2 comma 5. That means there are 2 rows and 5 columns, right? Now in this, a scalar can be any value. It can be like 12 or something. So if I write print, okay, x plus 12, it will broadcast 12 to become a matrix that is 2 cross 5. So it'll like 12, 5 times, right? Multiplied by 2. So it's going to create a whole matrix and it's going to add the two matrix as if they were the same. So when I'm doing this, essentially, I'm just adding 12 to everything. It's as good as saying this 12 is actually a matrix Y, which is basically doing this 12, 12, 12, 12, 12. And you might think this is pretty obvious because it is happening, but later on it will form an important concept. 12, oops, 12, and 12. So basically, if I were to do print x plus 12 or print x plus y, you would get the same result, right? Oops, wait. My bad. I need to do torch.tensor. Completely forgot torch.tensor, right? So here the scalar value has been added, right? And same way, if we do, it's the same as doing print of x star y as well. Star is multiplication, right? Print of x, oops, x star. Okay. So this will give the same value, the very same value it will give you, no matter what you do. Now, what we want to do is we want to understand that this is broadcasting with scalars, right? So now we will say broadcasting one-dimensional matrices to two-dimensional matrix. Okay, so you can always do it from a one dimension to n dimension pretty easily because it will just broadcast as long as one dimension. So the rule is as long as the 1D matrix that you are broadcasting is the same or has the same dimension along one of them. So for example, over here we have got print x dot shape, right? And let's say m comma n. So we can say m comma n is equal to x dot shape, right? And we can put this in a tuple for now. One sec. There you go. Yeah, we can do this. Actually, we don't even need to put it in a tuple. We can just expand it. Why do we need to do that? So we can actually just print here m n. Okay. So 2 comma 5, that's m cross n. So whenever I'm doing it, I need a matrix which is either 2 or 5. Then only I'll be able to do it, right? So if it's 2 and if it's vertical, then I can broadcast. If it's 5 and it's horizontal, then I can broadcast. Does that make sense? That's it. Those are like two main rules that you need to know. And if it's a single dimension, it will broadcast over anything, right? As long as these things are satisfied, it will work. Otherwise, it won't work. These are a few things that you need to know. Just to illustrate the example very quickly, I will write this. I'm going to just write it as matrix is equal to x. Okay, so then we will write over here as vector is equal to, so maybe I'm going to do it 5. So I'm going to do it as 3, 4, 5, 6, 7, 1, 2, 3, 4, 5. Yeah. And now what I'll do is, I completely forgot. I have to do torch tensor. Sorry for that. So I'm going to do tensor of this, right? And then all I can do is I can just write over here print x plus vector, right? See, these are this is actually very basic. It's very simple. So again, 4, 6, 8, 10, 12, 9, 11. So it's just adding the value of 3, 4, 5, 6 to 1, 2, 3, 4, 5. And you can see the output tensor. And if you also observe, it is duplicating this along the rows, right? Same way, if I write over here vector 2, okay, is equal to torch dot tensor of a matrix which is, let's say, 2, okay, and comma. So this is a two-dimensional matrix. So it's 1, 1. So it's 2 comma 0. Okay. So if you write over here the shape, you will get a number of rows and a number of columns. So it will be 2 comma 0. Sorry, 2 comma 1. Right? So wait, what did I do? Has not test snap. Why do I do this? Tensor. Right? And if you were to do that, I will actually also go to the x one. I'll just write x plus vector 2. Okay. Have a look. So now you can clearly see it is 2 comma 1. It's 2 rows. Whereas the previous vectors, if I will try to print vector shape. I do a lot of typos, I feel. So you can see it's 5. It's just start size is 5. Here it is 2 comma 1. But you see the difference. It's actually 5 comma 1. You could call it because it's just 1 wherever in every other dimension. But that's about it. So this is 2 rows, 1 column. Okay. And now that you know this, you can do scalar and vector, and you can broadcast. And just to summarize the rules, I will just type it down. So going by this example, for example, broadcasting dimensions are equal. One dimension is 1 or one dimension doesn't exist. So for example, I say a vec is equal to a vector of 1, 2, 3, 4, right? This is torch.tensor of that. And let's say b vec is equal to torch.tensor of, but this time, this guy is blessed on the vertical axis, right? So I will put him as 3, okay, comma 3, okay, comma 3. So now if I were to add this, what do you think is the value? What is the shape? So if I were to say print avec dot shape and print bvec dot shape, then I will write over here print avec plus bvec, and then I will write over here print cvec dot shape. Okay, so I will write over here cvec is equal to avec plus bvec. That's it. So I'll just this is cvec. Okay. So now, what do you think is the value of cvec? What will be the dimensions? So actually, from the broadcasting rules, you have to broadcast each. So this we can clearly see is equal to what is it, guys? It's actually 4 is what you would say. But ideally, what is it? There's just 1 row and 4 columns. So what would it be? It would be 1 comma 4, right? This is the shape. What would be the shape of this? There are how many rows? There are 3 rows. And how many columns? 1 column. It's 3 comma 1, right? So what would be the resulting shape of cvec? This will actually get broadcasted. So this will get broadcasted across 4 dimensions. So after broadcasting, it will become broadcasted bvec will become actually, it'll just get broadcasted to this. I will show it to you. 3 comma, whoops, what did I say? 3, this whole thing. I know this stuff is a bit weird, but this is basically how it will get broadcast. And avec broadcasted will be torch.tensor 1, 2, 3, 4, comma 1, 2, 3, 4, comma 1, 2, 3, 4. This is basically what will happen in a nutshell. Oh, and by the way, it won't exactly be like this because there is only 1 row. It's going to generate 3 rows. And because there is only 1 column, it will actually generate 4 of these. Does that make sense? Do you guys understand broadcasting? This becomes 4. Each of these becomes 4. So then actually, if you look at CVEC, then you write over here, print A broadcasted plus AVEC broadcasted plus, one second, whoops, plus BVEC broadcasted, you will get the same value. Okay, so just have a look. Okay, I think we did a small bug. Print AVEC broadcasted unsupported operate for type. Oh, my bad. I have to do torch tensor. How could I forget torch tensor? Okay, so there's updated value, and now you can clearly see the values are the same. Both of them are the same, and the broadcasting has happened exactly how I told you. So this 1, 2, 3, 4. So the final shape of CVEC, as we can predict, is going to be 3, 4. So dimensions are equal, or one dimension is 1, or one dimension doesn't exist. Then you can do it. So when one dimension doesn't exist, it's the same as broadcasting with a scalar. Otherwise, it is broadcasting across. So now that you know the basics of broadcasting, I would suggest you to practice this a bit. But yeah, this is the basics of broadcasting. So it'll expand it such that the dimension which is equal to 1 will expand to the other dimension, right? But this wouldn't have worked if it was 3, 2, it wouldn't have worked. You need one dimension is equal to 1, or one dimension that doesn't exist. If one dimension doesn't exist, that means the dimension is equal to 1 at that mark, right? Or dimensions are equal. So if it's 3, 2, and this was, let's say if this was 2, 4, and this was also 2, 4, this was, what do you call? If this was 2, 4, then you needed to have 2 at least in this, in the same dimension as it was. So one of those dimensions need to match. Then it will broadcast. Otherwise, it won't. At least one dimension must match, right? So this is the rule, and yeah, I think that's about it. You can go to a more complex shape, and you can think of, a vec is equal to like a 4-dimensional vector. So you can do torch.random 2, 3, 4, 2, right? This is like a huge vector. So if you write print a vec, you will get a huge value, right? And now if I write bb vec is equal to torch.random of torch.random off. But here what I do is I'll just keep one dimension the same, and second 2, 1, 3, 2, 4, 3, and here 2, 2. So this is there. This will still not work. This will not work. So if you look at this, they say print a vec plus bb vec. It won't exactly work because the dimensions aren't equal. You will see what I mean. Okay. Size of tensor 4 must match size of tensor B at non-singleton dimension 2. So there can be only one dimension which is changed. That's all you should know, right? In very large this thing. But if this was like this was 1, 1, that is 2, 3, and over here it was 1, 1. Now this would work. See? And that's because one of the dimensions is 1, 1. Do you see what I mean? You will need some practice with this, but once you do it, you should be good. So this is broadcasting, a revision on how broadcasting works in scalars and in vectors. Right? Hope you liked it. Let's go to the next chapter after this.